Hello, class. Okay, so a new problem with calculating the electric potential, where we have this like a washer. So it's a disc with a hole in the middle, and it has a total charge Q, which is distributed, between A and B, the inner radius and the outer radius, so that the charge density is proportional to 1 over r cubed. And what we want to do is find the potential at the center of this washer. So, like at any radius r, if you look at a little bit of charge there, it's inversely proportional to the radius cubed. But the total charge, so basically we're going to have to integrate from the inner radius to the outer radius to find out what k is. And once we have k, then we can find the potential at the center. So yeah, to start with, let's find out what this constant k has to be. So let's look at a thin ring at a radius r. And it has a thickness dr. So the thickness of this ring is dr. And again, this is a flat plane. Yeah, like a spherical surface would look just the same because the cross section would be circular. But it's a flat plane. And so the amount of charge, we can say that the area of this little ring at a radius r with a thickness dr, that area dA would be 2 pi r times the thickness, which is dr. So again, that only works if dr is very small. And of course, we're taking the limit that dr goes to 0, so this works. And so the charge contained in that little ring would be sigma times dA. So we have k over r cubed times 2 pi r dr. Now this k, of course, is not Boltzmann's constant, that 9 times 10 to the 9th. It's just some unknown k. So let's clean this up a little bit. We have 2 pi k dr over r squared. So you have 2 pi k, then r cancels out. So that's dq, the amount of charge contained in this very thin ring at a radius r. And if we integrate this from a to b, we get q would be, let's integrate so we can take out the constant. And we're integrating from A to B. So Q is some known value. We could give it a number, but let's just leave it general. Q is some known value. And this integral is easy. Minus 1 over r which we evaluate from A to B. Let me move this over. Okay, so Q is 2 pi k, and then we have minus 1 over b, and then minus negative 1 over a, so that'd be plus 1 over a. And so we can, let's actually combine this fraction. We have 2 pi k times b minus a divided by ab. And so now we can solve for k. So k would be ab times q divided by 2 pi b minus a. So just a quick review of what we've done. We considered a ring and a radius r with a thickness dr, and the area of that very thin ring, you can just think, just like unrolling it. And again, that only works for a thin ring. If you tried to do that for the whole washer, if you unroll it, like the inner circumference would be very different than the outer circumference. So that would not work for like the whole washer. But if there's not much difference between the inner and outer radius, that's very close to being accurate. And of course we're going to integrate, so we'll take the limit that dr goes to 0, and this becomes exact. And so dq is sigma dA. So we don't know what k is though at this point, but we know if we integrate dq from a to b, we get the total charge. So that allowed us to find this relation between k and q. And so now I'm going to erase this. We could write sigma now is abq over 2 pi b minus a times 1 over r cubed. So we have a constant times 1 over r cubed. And now what we want to do is we want to find the potential at the center of this ring. So let's clear this. Okay. So again, let's find the potential due to this little ring at radius r. So for a point particle, the potential is just keq over r, where is the distance from that point to where you're evaluating the potential. Now, for this ring, even though it's a horrible drawing, every point on the ring, so like normally what we'd have to do is we'd have to break it up into like individual pieces, and then we'd have to integrate going around the ring. And then once we have this completed ring, then we can integrate from A to B to like add up all these rings of different radii. But the potential here, like the potential due to each point on the ring is the same. So we can just treat it, like the actual location of the charge on this ring doesn't matter. So we can treat it as if there's a total amount of charge, which we know, dq would be sigma dA, which we already know the area is 2 pi r dr. So again, nothing new, except this time we know what sigma actually is. So, and then let's just integrate this. The potential due to that ring at a radius r. So here, this ke is different than this k here. So we have ke dq over r. So let's kind of put this together. We have ke dq is 2 pi sigma r dr divided by r. So that cancels out. So we have 2 pi ke sigma dr. Let's use this result that ke is 1 over 4 pi epsilon naught. So 2 pi ke is 1 over 2 epsilon naught. So yeah, if we multiply this by 2 pi, the pi cancels out. So we have 1 over 2 epsilon naught. And then sigma so we have dV, the potential due to this ring here, 1 over 2 epsilon naught. That was this part. We plugged in sigma, ABQ over 2 pi b minus a. And then we have the r cubed on the bottom, dr. So like everything over here is a constant. And yeah, I probably shouldn't have converted to epsilon naught, because now we're back to having a 4 pi epsilon naught. So it'd actually be easier just to leave it how it was. So we have here, this whole thing here, 4 pi epsilon naught, that's just Ke. Let's write it this way, r to the minus 3 dr. And now to find the potential for the entire ring, we just add up all these rings at different radii. So that's integrate. So all this comes out of the integral. And then we integrate r to the minus 3 dr from a to b. And that's a well-known integral. So integral of r to the minus 3 is r to the minus 2 divided by minus 2. So yeah, let's check that. Yeah. Okay, and then we just plug in the limits. And so this is a potential just at the center of this washer. Now, I can do like minus 1 over 2b squared. And then minus negative 1 over 2a squared. So we can simplify this a little bit. We can say we can take that common factor of 2 out of here. And then we have one over a squared minus 1 over b squared. I think we can clean this up a little bit. So I'm going to erase a lot of this work because I'm out of room. This is fine how it is, but we can clean it up algebraically, I believe. So let's do that. Let's see. Let's just get the... It's being recorded, so... Okay, so we have Ke ABQ over 2 b minus a. And I'm going to write this as b squared minus a squared over a squared b squared. So again, it's just multiply this one by b squared over b squared, this one by a squared over a squared. We have that common denominator. And we can get a little cancellation here. So b squared minus a squared, that's b minus a times b plus a. Could have canceled that out earlier, but so we can get some cancellation there. Get that to cancel out. I think that way is a little bit nicer than what we had down there. So I'd probably just leave it like this then. So yeah, one of these b minus a terms canceled out. We had ab over a squared b squared, so that canceled out. And one more thing I want to do with this, let's just check the units. So ke, yeah, you can kind of tell, these are all, a and b are distances. So we have keq over 2 times a distance squared times a distance. This is going to be like keq. We don't care about the 2, that's dimensionless. So like b minus a over ab, that's going to be some kind of a length. And so if you look at the potential for a point charge, we have keq over r. Those are the right dimensions. It has that constant k times q divided by a length. So that's the potential at the exact center of this washer with inner radius A, outer radius B. Okay, so again, doing these integrals to find the potential due to a charge distribution. Again, kind of a nice thing about that is that we're dealing with a scalar function potential, so we don't have to worry about directions or anything like that. So these integrals usually aren't too bad for the kind of things that we do in this class. All right, so that'll be it for this video.